In this section, we're going to talk about Landis rule. Landis rule is a rule that helps you the direction of the induced current when a voltage is induced in a coil. Okay, so let's state the rule. It says the direction of the induced current is in such a way as to oppose the cause. This rule states that the direction of the induced current is in such a way as to oppose the cause. Okay, this basically has to do with the negative sign in Faraday's law. So we're just going to demonstrate this by means of some examples. Okay, let's consider the first example. Now suppose we have the following permanent magnet. Okay, let's say this is the permanent magnet. Let's say this end is the north pole and this end is the south pole. Now we know that magnetic field lines, they come out of the north pole and they go into the south pole. Okay, that means the direction of the magnetic field is this way. It comes out of the north pole and comes on in the south pole. Remember, magnetic field lines form complete loops, so they're just making complete loops like this. Now suppose we have a loop over here, a conducting loop, okay, like this. All right, now the question is, determine the direction of the induced current in the loop when the loop is pushed towards the magnet. Pushed towards the magnet. Okay, now we have this loop. We want to find out whether the direction is clockwise or counterclockwise when this loop is pushed towards the magnet. So what is the cause for change of flux when we push this loop towards the magnet? You see the magnetic field decreases as you go farther and farther. So as the loop gets closer and closer to the magnetic field crossing it increases. So the cause of the change in flux when this loop is pushed towards the magnet is the increase in magnetic field. So first we have to identify the cause. Remember, Landis rule says the direction of the induced current is in such a way as to oppose the cause. So first we have to identify the cause. So what's causing the change in flux when this loop is pushed towards the magnet is the magnetic field is increasing as the loop is getting closer and closer to the magnet. So let's identify the cause. The cause is increase in magnetic field. Increase in magnetic field as it pushes closer and closer towards the magnet. Okay, now what's going to happen as the loop is pushed, the flux will change, and the change in flux will produce induced voltage, and the induced voltage will produce current. Okay, so we're trying to find out whether the current is clockwise or counterclockwise. Now that current, that induced current, is going to produce its own magnetic field. Okay, so the current in this loop is going to produce its own magnetic field. So let's call that the induced magnetic field, or B induced. Okay. Okay, so this will produce its own magnetic field. Let's call it induced. Now the question is, should the direction of that induced field be this way or this way? Okay, that's where Lensor comes. The cause is increase in magnetic field. So the direction of the induced current in this loop must be in such a way as to decrease the magnetic field. Therefore, the direction of the induced field induced by the induced current should decrease the magnetic field, should be in such a way, in such a way as to decrease the field, such a way as to decrease the field. That's the external field, the field produced by the magnet, the field due to the magnet, okay, due to the magnet. Now we're talking about this field over here, the field produced by the current in this loop, and that current is produced by the induced voltage. All right, so we've concluded if the effects increase, then the effect of this should be to decrease it. To decrease it, should it have the same direction, this one, or opposite direction to the magnetic field? If it's to decrease it, it should have opposite direction. Okay, so in order to decrease the magnetic field, then the direction of the induced field should be this way. Okay, so the direction of the magnetic field this way, and it's increasing. So the effect of the current over here, or the magnetic field, this is the induced current over here, must be in such a way as to decrease it. And to decrease it, it has to oppose it. Okay, so the direction of the induced magnetic field due to the current over here should be to the left. And then if you remember, the current and the field are related by the right hand rule for the field due to a coil. Okay, that is, if you wrap your fingers around the current, then time gives you the direction of the magnetic field. Now we know the magnetic field is to the left, like this, so the current should be clockwise. Okay, therefore the direction of the induced current as seen by an observer on this side is clockwise. So this implies to decrease the magnetic field. This implies, since the direction of the magnet field is to the right, the direction of the induced field should be to the left to decrease it. The direction of the induced field should be to the left, to oppose it. Okay, and from the right hand rule, if the field is to the left, the direction of the induced current should be clockwise. The direction of the induced current should be clockwise. Okay, this is the right hand rule. The field is to the right, so the current is clockwise. All right, so let me revise it again. So you got this loop, push it towards the magnet. Okay, so as the loop is pushed towards the magnet, the flux will change. The reason the flux will change is because the magnetic field crossing this loop increases as the loop is pushed closer and closer to the magnet, because the magnetic field increases as you get closer and closer, right? Therefore, the cause is increase in magnetic field. Now, that change in flux, according to Faraday's law, will produce induced voltage, and that induced voltage will produce an induced current. And that induced current should produce its own magnetic field. That's called induced magnetic field, okay? Now, the direction of that induced magnetic field should be in such a way as to decrease the magnetic field, because the cause increase. If the cause increase, then the effect of this field should be to decrease it. And to decrease it, it has to oppose it. So since this field is to the right, the induced field should be to the left. And then we use the right hand rule. If the field is to the left, then the current should be clockwise. Okay, let's look at another example. Okay, let's say we have this magnet over here. Now let's say this is the south pole, this is the north pole, okay? Now the magnetic field will look something like this. And remember, magnetic field lines, they come out of the north pole, they go into the south pole. So in this case, the arrow goes this way. The direction of the magnetic field is toward the left, okay? Now suppose we have a coil over here, a conducting coil, okay? Now suppose the coil is pulled away. Suppose the loop is pulled away. The loop is pulled away. Okay, the question is determine the direction of the induced current. Maybe let's do step by step. First, let's say A. Determine the cause. What is the cause for the induced voltage as it is pulled away? Induced voltage as it is pulled away. Okay, what is changing? What is changing the field? As the loop gets farther and farther, you see the magnetic field crossing it decreases. So the cause is decrease in the magnetic field as it gets farther and farther from the magnet. So the cause is decrease in the magnetic field crossing it as it is pulled away. Okay, so in this case the cause is decrease. As it goes farther and farther, the magnetic field crossing it decreases. Okay, now that change in flux will produce induced voltage, and that induced voltage will produce induced current, and that induced current will produce its own field. Okay, now B, let's say determine the direction of the induced magnetic field. The direction of the magnetic field due to the induced current. Okay, so we're going to have induced field over here due to the current. The question is, should that field be this way or this way? That's where Lenz's rule comes in play. Okay, now Lenz's rule says the direction of the induced current must be in such a way as to oppose the cause. The cause is decrease in the magnetic field. Therefore, direction of the induced field is must be in such a way as to increase the field. Therefore, direction of the induced field should be, since the cause decrease, to increase or to help the magnetic field is a magnet, the magnet field, to increase the field due to the magnet. Okay? And to increase it, it has to be parallel to it. To increase it, it has to be parallel to it. It has to be parallel to it. Okay? But the direction of the field is to the left. Okay? So that means the direction of the induced field also has to be to the left to increase it. Okay? To increase it, it has to be to the left. Okay? That's the direction of this field. All right? Therefore, since the magnet field is to the right, to the left, the magnet field is to the left, the induced field also should be to the left. The induced field should also be to the left. Should also be to the left. Okay? So now we have determined the direction of the induced field is to the left. And then we determine the induced current from the right-hand rule. That is, the right hand says if these fingers are current, time gives you field. That's the right-hand rule for the magnetic field due to a circular loop. Okay? All right. And then let's say determine the direction of the induced current in the loop. The direction of the induced current in the loop. Okay, so the answer is, using the right hand rule, when the field is to the left, the direction of the induced current should be clockwise. So from the right hand rule, when thumb points left, the induced current should be clockwise. The induced current should be clockwise. The induced current should be clockwise. So usually right is related with counterclockwise and left is related with clockwise. Okay? Let's look at another example. Now suppose we have a U-shaped conductor like this. This is a U-shaped conductor, and let's say that's placed in a magnetic field that is perpendicularly out like this. All right, and then let's say we have this rod over here. Now suppose this is pulled, let's say to the right with an external force. It's pulled to the right with, let's say, with an external force. Okay, it's being pulled by an external force, let's say pulled. So as you've seen before, this is the loop now. Now as the rod slides in the U-shaped conductor, the area increases. Okay, and the increase in the area changes the flux, and the change in flux produces induced voltage. The induced voltage produces induced current. So what we want to find out is the induced current flowing counterclockwise or up the road, or is it going clockwise or down the road? Okay, that's what we're trying to find out. Okay, so determine the direction of the induced current, let's say in the rod. Okay, so to apply Lenz's rule, first we have to identify the cause. So let's say, what is the cause for the change in flux that produces the induced voltage? Okay, the cause is this external force which is pulling the rod and increasing the area. Okay, so the answer is the external force. The answer is the external force that is increasing the area, that is increasing the area of the loop. Okay, that's the cause of the loop. All right, so now what's going to happen is we have, as the area increases, there will be change in flux. The change in flux will produce induced voltage, and that induced voltage will produce current. So we have a current carrying rod placed in a magnetic field. And as you remember, a current carrying rod placed in a magnetic field is acted upon by a magnetic force. Now the question is, what should be the direction of the magnetic force acting on the rod? Okay, so determine the direction of the magnetic force acting on the rod due to the induced current in the coil. Okay, so now we have to use Lenz's rule. The cause is the external force, right? And so the direction of the induced current should be in such as opposite the cause. So direction of the magnetic force, you see this is the field and this is the current or the rod. Okay, so the magnetic force is perpendicular to the plane determined by the rod and the field. In other words, it's either to the left or to the right. Okay, so should it be to the left or to the right? Now from Lenz's rule, we know that it has to oppose the cause. So since the cause is pulling it this way to the right, then the magnetic field should be to the left. Okay, that is conclusion from Lenz's rule. Since the external field is pulling to the right, then the magnetic force should be pulling to the left. Okay, now the answer is, since the external force is to the right, okay, according to Lenz's rule, it has to oppose the cause. According to Lenz's rule, the direction of the magnetic force should be to the left. The direction of the magnetic force should be to the left. The opposite should be to the left. Okay, so now we know the direction of the force is to the left, which is this one. We know the direction of the magnetic field is perpendicularly up. Okay, remember when you apply the right hand rule, this one is current, this one is force, this one is field. So what we have is we have the force is this way, the magnetic field is up, so I don't know how to write. So we've got the field, the force going this way. I should do like this. Okay, I don't know if you can see that over here, but so this is the force which is to the left. Again. So this is the magnetic field, this is the force. Okay, so the force should be this way, the magnetic field should be this way, the magnetic field should be this way. So you see that? That's the situation. We have the force to the left, the magnetic field perpendicularly up. So this one is the direction of the induced current. So the direction of the induced current from the right hand rule should be down. Okay? So the direction of the induced current is down the road. So from the right hand rule or the screw rule, the direction of the induced current should be down the road. So let's say D, determine the direction of the induced current, the direction of the induced current. Okay, so since the force is to the left, since the force is to the left and the field is perpendicularly out, the field is perpendicularly out, okay, from the right hand rule, the direction of the induced current should be down the road. The direction of the induced current should be down the road, yeah. Down the road. Okay. Now let's look at another example. Now suppose we have a solenoid. Okay, so let's say we have like this. Let's say this is the source or the battery. So the direction of the current is going to be this way. Okay, direction flows from positive to negative. So it's going to be the direction of the current. All right. Now suppose we have another loop concentric with it, like this. Okay. Now let me put a switch over here. Suppose we have a switch over here. Okay. Now, suppose the switch is suddenly closed. What happens? The current increases from 0 to a certain value. Okay. So what's going to happen is, you see, the magnetic field crossing this loop over here increases. The magnetic field is like this. Now we can determine its direction from from the right hand rule, so fingers are counterclockwise, the field is to the right. So this is the direction of the field. Now determine the direction of the current in the loop. This is the loop I'm talking about, the loop over here, okay, and the switch is closed. The switch is closed, okay. So as the switch is closed, the current increases, okay. So as the switch is closed, the current increases. So the cause is an increase in the current, but if you remember, the magnetic field inside over here is proportional to the current. You remember this formula? B equals mu naught number of turns divided by the length solenoid times current. So B is proportional to the current. So as the switch is closed, the current will increase from 0 to a certain value. So the cause is an increase in magnetic field, okay? So as the switch is closed, the current increases all of a sudden. The current increases from 0 to a certain value, okay? From 0 to a certain value, okay? Which means magnetic field increases, okay? That is, field increases, okay? So the cause is an increase in the magnetic field in the solenoid, okay? So the cause is increase in the magnetic field crossing the loop, and the magnetic field is the magnetic field due to the solenoid, or due to the current of the solenoid, okay? So the cause is increase in magnetic field, okay? So as the magnetic field increases, the flux crossing this loop increases, okay? And that increase will produce induced voltage, and that induced voltage will produce induced current, and that induced current will produce its own field, okay? This loop over here will produce its own induced field. So the question is, should the direction of the induced current be to the left or to the right? Now this field is to the right, and the cause is increase in magnetic field, okay? So the direction of the induced field must be in such a way as to decrease the field. This implies the direction of the induced field should be in such a way as to decrease the field, okay? And to decrease the field, the induced field should have opposite direction to that of the solenoid field. To decrease the field due to the solenoid, okay, the direction of the induced field, okay, should be opposite to that of the solenoid field, should be opposite to that of the solenoid field, okay? So the solenoid field is to the right. Therefore, the direction of the induced field should be to the left. Okay, so the direction of the induced field should be to the left. This implies direction of induced field is to the left. Direction of induced field is to the left. Okay, and from the right hand rule, the direction of the induced current in the loop should be clockwise. Induced current in the loop should be clockwise. All right. So the induced current is clockwise. You got left, so this should go clockwise. So that is the direction of the induced current. Next, we're going to look at a generator. A generator is a device that converts mechanical energy to electrical energy. This is a device that converts mechanical energy to electrical energy. Its basic components are a coil and a permanent magnet. Okay, basic components are a magnet and a coil, a permanent magnet and a coil. Now let's see how it works. Suppose, let's say we have this two magnets. Let's say this is the north pole, this is the south pole, so there's a great field like this, field going like this. Okay, now suppose you have a coil in here, a coil like this. Let's say the direction of the area is something like, let's say this is the direction perpendicular to the loop. Let's say the direction of the area. Okay, so as the coil rotates, let's say the coil is rotating like this, you see the direction, the field has a constant direction, you see, but as the coil rotates, you see the direction of the area rotates. Okay, so what happens is when the coil rotates, the angle between the field and the area of the loop changes, and that's what causes a change of flux. Okay, and that flux produces induced voltage. That's how we get electrical voltage out of a coil rotating in a magnetic field. Okay, so as the coil rotates, the angle between the area of the loop, the area which is perpendicular to the plane of the loop, the area of the loop and the field changes, and the field changes, and that's what causes the change in flux, and that change in flux produces induced voltage. This is how a coil rotating in a magnetic field will produce electricity or induced current. Okay, so something has to rotate this coil. Okay, it could be rotated by hydroelectric power or something else. So we're converting the mechanical energy of this coil to electrical energy. You rotate this with this mechanical energy, and that will be converted to electrical energy. Okay. Now let's say the angle between the field and the area. Let's say this is the field certain time, and this is the area. Okay, it's angle theta. Now the coil rotates. If it is rotating with angular speed omega, if it is rotating with angular speed omega, then you see this angle increases with time. Theta equals omega times time. So our angle is omega times time. Okay? So the flux per coil, flux, that's if we've got only one coil, would be the magnetic field times the area times the cosine of the angle, which is increasing as a function of time because it's rotating. So this will be omega t. Okay, this is flux per one coil. If there are n coils, then it should be n times. If there are n coils, then we have to multiply by n. So the total flux would be n b, area of the loop, and then cosine of omega t. Okay, so the A is the area of the loop, B is the field, n is number of turns. Okay, so in this formula, n is number of turns. Okay, A is area of a coil, and of course omega is angular speed, the speed by which it's rotating, and t of course is time. Okay, now let's apply Faraday's law. Now I cannot do this without calculus, so I'm going to use calculus. Hopefully some of you are familiar with calculus. So the induced voltage, which says the rate of change of flux with respect to time, in the language of calculus is the negative of the derivative of the flux with respect to time. Okay. I'm sorry if some of you are not familiar with derivatives, but I have to do it over here. So the induced voltage is the negative of the derivative of the flux, which is nBA cosine omega t. All right. So we take the constant out, negative nB times area, and then the derivative of cosine omega t. For those of you who are familiar with calculus, this derivative is negative omega sine omega t. So we get the induced voltage is nBA omega angular speed times the sine omega t. Okay, so this gives you the formula for the induced voltage would get by rotating a coil inside a magnetic field. Okay, so if you plot this induced voltage as a function of time, let's say this is induced over here and this time over here, so it's the same function. So the maximum value is this one, the amplitude, and then we'll go like this. We'll go like this. Actually, if you look at the voltage that you get from the wall outlet, if you connect it to a computer, that's what it will look like, because it's produced by rotating a coil inside a magnet. So this value over here, the maximum value, this is the amplitude. So this maximum value over here would be NBAW. So the amplitude of the voltage that you get over here is the product of the number of turns, the magnetic field, the area of the loop, and the angular speed. And this interval over here, this is a period, time taken for one cycle. That's the period, and then of course that's 2 pi divided by the angular speed. So you see, the maximum value or the amplitude equals this one. Therefore, the maximum value, maximum value or amplitude of the voltage is given by the following formula. This is the max or amplitude, and that is NBAW. Okay. Example. Okay. Let's say a coil of, let's say, of width maybe 0.2 meters and length, let's say 0.4 meters, is, let's say, rotating in magnetic field, let's say 10 Tesla, with an angular speed of, let's say, 10 radians per second. Okay, so A, calculate the amplitude of the voltage, amplitude of the induced voltage, So in this case, we're looking for the max, okay, the amplitude. So it's going to be something like this. We're looking for this one, which is MBAW, okay? This is MBAW. So the the maximum value of the induced voltage is NBA angular speed, okay? Now the number of turns is 100. You see the area is 0.2 times 0.4. The area of the coil 0.2 times 0.4, which is 0.08. The magnetic field is 10 Tesla, and the angular speed is also 10 radians per second. Okay, so we just multiply. So the induced voltage is 100 for the number of turns, 10 for the magnetic field. The area is 8 times 10 to the power negative 2, and the angular speed is 10. Okay, so from the numbers we get 8, and then you've got 1,000, 10,000, that's going to be times 100. So the amplitude of the voltage is 800 volts. B, calculate the time taken for one cycle. Calculate the time taken for one cycle. The time taken for one cycle. So in this case, we're calculating the period. Okay, so we're looking for the period, question mark, but we know that the period is 2 pi divided by angular speed. The angular speed we just saw is 10 radians per second, so that is 2 pi divided by 10, or pi, or 5 seconds. Okay. Next, we're going to look at inductors. Inductors, this is one of the important circuit elements in electronics. There are 3 very important circuit elements in electronics. They're the resistor, the capacitor, and the inductor. We have already discussed the resistor and a capacitor. This is a 3rd important circuit element, and it's called an inductor. Okay, so this is simply a coil. An inductor is a coil, just like a solenoid. This is inductor is a coil. Is a coil, just like a solenoid, Okay, the circuit symbol for solenoid is simply a coil. This is a circle symbol of an inductor. All right. Now, maybe let me go to the other side. Let's see what happens when the current in a coil changes. Okay, suppose let's say we have this coil or solenoid, okay, like this, okay. Let's say our solenoid like this, and let's say we have current flowing through it. Okay, so the current will go this way, and then from the right handle that will produce a field that goes like this. Okay, now the question is, what happens when the current changes? Okay, now you see this coil over here is being crossed by its own magnetic field, so it has magnetic flux because of its own field. Okay, now if we change the current over here, the field over here changes, so there will be a change in flux crossing this solenoid because of its own field, and that change in flux will produce induced voltage in the solenoid. Okay, now since this induced voltage is produced by its own current, it's called self-induced voltage. Okay, now as the current in the solenoid changes, as the current in the solenoid changes, its magnetic field changes. Its magnetic field changes. Okay, so that means the magnetic field, the magnetic flux, its own current change. So the magnetic flux due to its own current, will change. Okay, and that change will induce voltage on the solenoid, and that change induces voltage on the solenoid or on the inductor. Now, since this induced voltage is produced by its own current, it's called self-induced voltage. Since this induced EMF is produced by changes of its own current, it's called self-induced voltage. It is called self-induced voltage. Okay, so we're going to use E self to represent it. Okay, so it's called the self-induced voltage. All right, now if you remember, the magnetic field is related with the current as follows: mu naught N over L times I. That is, these are constants. Okay, so that implies the magnetic field is proportional to the current. Okay, the magnetic field is proportional to the current, and the flux which is B times A. Okay, A is a constant, B is proportional to I. Okay, this implies the flux is proportional to the current. Now the induced voltage or the self-induced voltage is equal to rate of change of flux with respect to time. Okay, and since the field is proportional to the current, it follows that the self-induced voltage is proportional to the rate of change of current. Okay, so the self-induced voltage, there's a negative over here, is proportional to the negative rate of change of current in the coil. Okay, so mathematically we can say that this self-induced voltage is proportional to the negative of change in current with respect to time. Okay, so that means is this ratio, what that means is this ratio divided by negative delta I by delta T is a constant. Okay, this constant is called the self-inductance of the coil. Okay, this constant is called the self-inductance of the coil. The self-inductance of the coil, and it's denoted by L. Okay, so we have the following formula. With that, we have the self-induced voltage is equal to negative L times the rate of change of current with respect to time. Okay, so L is, or this inductance is to a coil as a capacitance is to a capacitor, or as resistance is to a resistor. Okay, now let's look at an example. Let's say the current in a solenoid, let's say increased, let's say from 2 amps to maybe 7 amps in 0.5 seconds. Okay, let's say if the average induced voltage, let's say self-induced voltage, let's say is 0.002 volts. Calculate the inductance of the coil. Calculate the inductance or self-inductance of the coil. Okay, so we have the current increased from initial current of 2 amp to final current of 7 amp in a time interval of 0.5 seconds, and during that time interval the average induced voltage was 0.002 volts. The question is, what is the inductance? Okay, so we have the self-induced voltage equals negative L times delta I by delta T. Okay. We're not interested in sine, so let me just put absolute value over here. Just put absolute value over here. Okay. So we're looking for L. So L is the self-induced voltage divided by the rate of change of current. Okay. Well, that would be E self over change in current times the time. Okay. So we have 0.002, and the change in current is 7 minus 2. This is a change in current, and the time interval is 0.5. Okay, 0.5. So this is 0.5 divided by 5, that is 0.1. So basically we get 2 times 10 to the power of -3. And the unit of inductance is Henry. I haven't stated that, but the unit of inductance is Henry. Unit of inductance, okay, which is volt divided by ampere times second, is called Henry and abbreviated by capital H. Okay, so this is 2 milli Henry. All right, let's look at another example. Let's say find an expression for the inductance, or let's say self-inductance of a solenoid of radius r, length L, and number of turns N. Now, this inductance is a property of the coil, which means it just depends on the geometry of the coil. It doesn't depend on anything else. So we should be able to find an expression for the inductance in terms of this geometric values. So we have a solenoid like this. Okay, we have this going on. Number of turns is N and so on. Okay, and the length is L, the radius is R. Okay, all right, so let's say we have power to the solenoid, and then we've got current this way. Okay, that will produce current that goes like this, and from the right handle the direction of the current would be this way. Okay, so let's try to get an expression for the self-induced EMF. Remember this is the formula for L. We've got negative L delta I by delta T. You can say L is the negative of the self-induced EMF divided by the rate of change of current with respect to time. Okay, now suppose the current over here is I. Okay, first let's obtain expression for the flux. The flux per turn crossing the solenoid, you see, it will be over here. The angle between the area and the field is approximately 0. You see the field is this way, the area is this way, so it's 0. So it's just me B times the area times cosine of 0. Okay, and the area of one coil is pi r squared, so this is B pi r squared. Okay, but if you remember, we can express the magnetic field in terms of current. B due to a solenoid is mu naught N over L times current. Okay, so the flux per turn, per one turn, is we've got mu naught n over L times current, and then times the area, which is pi r squared. Okay, and the total flux, if there are n turns, if there are n turns, and then this equals n times flux per turn, right? So the total flux would be n times this expression over here, that is mu naught n over L times current for the field, and then we have pi r squared for the area. Okay, so we can simplify this one. It is mu naught, we've got the square of the number of turns divided by the length, and then you got the area, and then you got the current. Okay, now let's look at the self-induced EMF. That is negative delta phi by delta t. Okay, now I see all this expression is a constant except the current. Okay, so this would be negative mu naught n squared over L times pi r squared rate of change of current with respect to time. Okay, so you see the self-induced flux is proportional to the rate of change of current. So it follows that this is the inductance. Okay, so you've got the inductance is E self-induced EMF divided by the rate of change of current with respect to time, maybe times the negative rate of change of current. When you do that, you just get this one, mu naught n squared over the length divided by pi r squared. So this expression over here gives you the inductance of the coil. So to obtain the inductance of a coil, all you have to know is the number of turns, the radius, and the length. It's a function of geometry of the coil.